Hello and welcome to the Zeus Power Podcast. Today we talk to Peter Foret, Chief Engineer at Zeus Battery Products. Peter will give us his history and initial interests in battery technologies and electronics, as well as the differences between SLA sealed lead-acid batteries and LFP lithium iron phosphate batteries, and the advantages and disadvantages for each chemistry. Peter will also be sharing some technical differences between energy efficiency, density, and capacity, and giving his insights into the development behind battery chemistries and the future of battery technology. Thank you, Peter, for joining us on the Zeus Power Podcast.
Hello, this is Peter Foret. I'm a Chief Engineer with Zeus Battery Products located in Bloomingdale, Illinois.
Can you give us some history on your expertise in and experience with batteries?
I had to learn in a physics class about an electrical coil and how fast changes in its electrical field lead to a counter-reaction generating a high voltage while using a relatively low voltage DC source. There was a battery. Learning about this, I had to build a portable shock box using a 4.5 volt zinc carbon flashlight battery. That was the only battery that was available then. A tuning coil that I had removed from an old radio receiver, and a variable resistor that I had taken from a slot car speed controller. Later in my life, while being part of a Standard Oil, now BP or British Petroleum or /Amoco, I have become part of the team working on the development of lithium iron sulfur rechargeable cell. My involvement then in the R&D project was in creating test fixtures, chargers, and active loads to support the lithium ion cell development. Interestingly enough, the cell factor selected then was called Sub-C lithium sulfur LIS batteries. Given their lightweight and theoretical high capacities, are a promising alternative to conventional lithium-ion batteries for large-scale energy storage systems and electric vehicles. But LIS, lithium-sulfur batteries currently suffer from poor longevity. This chemistry is still being under development.
Could you define SLA or sealed lead-acid battery technology and its advantages and disadvantages?
SLA batteries are available in all shapes and sizes, and they do not require any maintenance through their useful life. SLAs are best in terms of reliability and working capabilities. These batteries withstand slow overcharging, long-term inactivity, and offer best value for power and energy per kilowatt hour. They offer one of the longest lives in a standby or low DOD, which is depth of discharge, applications. About 97% of lead can be recycled and reused in new batteries together with their plastic case and acid that can all be recycled. SLA batteries offer some of the lowest self-discharge rates amongst rechargeable batteries. They offer good performance at extreme temperatures. Here are some disadvantages of SLA batteries. They are heavy with low specific energy and a poor weight-to-energy ratio. They also take a long time to fully charge. They take up to 16 hours from fully discharged state to get fully charged. SLA batteries must be also stored in a charged condition in order to prevent sulfation and thus capacity degradation. They have a limited cycle life that can heavily depend on the rate of discharge. Repeated deep cycling significantly reduces the battery life, thus their cycle life expectancy is lower than other rechargeable batteries. Lastly, they are not very environmentally friendly as you imagine due to the lead and acid content.
Could you define LFP or lithium iron phosphate battery technology and the advantages and disadvantages to that chemistry?
LFP, lithium iron phosphate, LiFePO4, is the safest lithium battery. They are offered as a drop-in for SLAs and have a very long life. LFP, lithium iron phosphate cells, are of a solid construction. Unlike SLA batteries, there are no fragile brittle plates that can be prone to failure over time as a result of vibrations. LFP cells do not contain any toxic heavy metals such as lead, cadmium, or any corrosive acids or alkalis, thus making them the most environmentally friendly battery chemistry available. LFP batteries can be safely and rapidly recharged. While fully discharged, the power cell-based LFP battery can be 85% charged in about 15 minutes. They offer high discharge rate capability, up to 10C continuous and 20C pulse discharge. LFP batteries have a very constant or flat discharge voltage similar to nickel-based chemistries. A voltage stays close to 3.0 volts during discharge until the battery is exhausted. This allows the battery to deliver virtually full power until it is discharged. This can greatly simplify voltage regulation in electrical circuits. LFP batteries do not suffer from thermal runaway like other chemistries do and can be operated in any orientation. They are virtually maintenance-free for the life of the battery. They can be used safely in high ambient temperatures of up to 75 degrees C without much degradation in performance. Unlike other rechargeable batteries, LFP batteries can be left in partially discharged state for extended periods without causing permanent damage. They offer very safe technology and will not catch a fire or explode while charging or discharging. They offer over 3,000 discharge cycle lives compared to typically around 500 cycles for lead-acid battery in the same application, thus providing good return on initial investment. LFP battery also lasts up to 7 times longer than lead-acid battery and about 3 times longer than the regular lithium-ion or lithium polymer battery. Due to the similar cell voltage, in most instances, LFP battery can directly replace lead-acid batteries. Because of the nominal 3.2 volt voltage, 4 LFP cells can be placed in a series for a nominal voltage of 12.8 volts. This comes close to the nominal voltage of 6-cell lead-acid batteries, which would be a 12-volt battery. Along with good safety characteristics of LFP batteries, this makes LFP a good replacement for any lead-acid batteries. LFP, lithium iron phosphate batteries, have higher current and peak power ratings than lithium ion and lithium polymer. LFP cells experience a slow rate of capacity loss, greater calendar life than lithium ion and LiPo or lithium polymer battery.
What's the difference between energy efficiency, density, and capacity? How do these qualities define an optimal energy source, and which battery can provide that?
If volume and weight are critical, lithium polymer or lithium ion based battery are typically the best choices. If power density and cycle life are leading factors, LFP or lithium iron phosphate may be the best choice. While for standby storage and deep discharge cycling applications where initial cost is critical, an SLA or AGM absorbed glass mat battery is the best choice. Zeus can help selecting the best chemistry based on the customer application requirements and their use case.
Thank you, Peter, for joining us today and giving us a fascinating look into the world of battery chemistries and what the frontier of battery technology looks like. And thank you, listeners, for joining us today. Subscribe to get notifications as soon as the next episode is released. Please visit ZeusBatteryProducts.com for more information on how to power your world. Please join us on the next episode of the Zeus Power Podcast.